Okay, so let's take a look here at the second question. So, the theme for this exam is sequences and series here. So, first question was on sequences, and now the second question is on series. So it's the connection between the two. A series is a big sum, and the terms in the series are a sequence. And then also you get a sequence of partial sums. Okay, so, all right. So enough jibber jabber. Let's go through and do these. So, geez, I'm going to change this. I made a mistake here. This one is supposed to be 2 to the n. Alright. So just to kind of reprocess number a and pretend like I had written this like that. So what is that? Let's just write down a few terms of that one, okay? So when n is 1 here, you've got 1/2. And then when n is 2, you've got 1/4. And then when n is 3, you've got 1/8. And then you've got 1/16 plus. Okay. So we gave several arguments for why all this stuff should add up to 1. But if you don't want to remember all those arguments, you can just see that this is a geometric series. And several other of these series will be geometric series, so maybe I should say what that is. So what is a geometric series? So a geometric series is a series of this form. So there's some number a and some number r. Okay, and r is raised to a power. A just kind of always sits there. And n goes from 1 to infinity. Okay, so in what way is a here a geometric series? Well, it's a geometric series. How can I think of it as a geometric series? So maybe, what happens if I let this run, right? So what if n equals 1 goes n, then r to the 0 power is 1, and so this is a plus ar plus ar squared plus ar cubed plus 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 plus. Okay, so you kind of want to say that, well, alright, so parsing this as a geometric series is maybe not exactly trivial. So how do I realize this as a geometric series? What I have to do is I have to think of it as missing a 1, right? Because it's like a is 1 and r is 1/2. Okay, why do I say that? It's because something is getting raised to the power n here. 1/2 to the n. It's the same thing as 1/2 to the n. Okay, and so what's happening, sorry, I don't know why I wrote 2 there, it should be n. So the thing that's getting raised to higher and higher powers is 1/2, and it's always being multiplied times this same thing, and so that's 1 because it's not really being multiplied by anything. Okay, so how do I realize this as a geometric series? I've already said that I'm going to do it like this. The problem is that there's supposed to be this term, right? There's supposed to be the term that's just a by itself. But if I do it like this, then this series is missing a 1. Okay, fine. So so what if I just do 1 plus that, n equals 1 to infinity of 1/2 to the n, then I get my nice geometric series, right? This is the same thing as the sum n equals 1 to infinity, and now I have 1/2 to the n minus 1, and great. Okay, it's because this thing is playing the role of 1/2 to the 0. So why did I go to all the trouble to put it in this nice standard form? It's because when things are in the standard form, we have the formula. Okay, so let me remind you that the geometric series, so if I have a geometric series a times r to the n minus 1, as n goes from 1 to infinity, this is equal to a over 1 minus r if the absolute value of r is less than 1, that basically means r is between 1 and negative 1, and it diverges otherwise. Okay, alright, so that's how geometric series work, and this is one. And so we use a equals 1, r equals 1/2, just a quick check that that the absolute value of r is less than 1, so it's definitely true for 1/2, right? Okay, so just use the formula. So using the formula, the answer here is just 1 over 1 minus 1/2, and if you do that out, you'll see that it's 2. Okay, super fantastic. Now how can I relate that back to the original question? Notice that I added a 1 here, right, to put it in the standard form. There are other ways to get around that, but for some reason that's what I did. So to get back to the original series that we were given, you just have to kind of knock this 1 off both sides, right? And what happens when you do that? You get that the original series is 1. You should just know that that's 1 anyway. Honestly, you should memorize that. Okay, so number 1 is done. And let's go on to number 2. So, B. So what does B have in store for us here? This is, let's try to find, we have to find the rule that determines this series. So what's making this series here? Let's try to understand it as a geometric series. So what's going on, what's happening with the denominators? They're going 3, 9, 27. So if I think of this as being kind of like 5 over 3 to the 0 plus 2 times 5 over 3 to the 1 plus, and now I've got 20. What is that? That's 4 times 5, right? 4 times 5 over 3 squared. And some of these are minus. Actually, this first one is minus. Okay. So I'm just trying to find what the regularity is here, and then I've got minus 40. Okay, so what is that? That's 8 times 5, right? 8 times 5 over 3 cubed. Okay. So what's the general form? What's the rule that's making these things? Seems like I've got 2 to some power times 5 on top, right? It's going plus minus, minus plus, I mean. So plus minus plus minus. That means there's probably negative 1 involved there somewhere. Okay, so if we're going to start at 1 and the first one's positive, then let's make this n plus 1 so that the first one is positive. And we've got, looks like 5 times 2 to the n would work, right? Because here I can think of n as being, well, I want to think of n as being 0 there. Okay, so we're imagining we're going to start at 1. So n equals 1 to infinity. Okay, so here this is like 5 times 2 to the 0. Here is 3 to the 0 in the bottom, so I can write 3 down here like this. 3 to the n minus 1. And this works. By Jove, it works. And in fact, maybe I could, it's a little simpler. I can kind of kill 2 birds with 1 stone if I rewrite it like this. It's like 5 times negative 2 over 3 to the minus n minus 1. And n equals 1 to infinity. And by gosh, it's geometric. It's a geometric series. Maybe you're saying preposterous. But it is geometric series because I have the a here, the constant factor is 5. Why did I write 1? Just to keep you on your toes. Okay, so the constant factor is 5, and then the common ratio, or the thing that gets raised to the power, is r, and r here is minus 2/3. Okay, so I've kind of erased everything that I said about geometric series, maybe. Well, actually, here you can see is the formula. Here's the constant part, here's the common ratio. Goes from 1 to infinity, and the common ratio starts at n minus 1. All those things are true. And it's also true that the absolute value of the common ratio r is less than 1, right? So just check. Here, the absolute value of r is less than 1. So what that means is that I can use the formula. And remember that the formula is a over 1 minus r. So in this case, this gives us 5 over 1 plus 2/3. So what does all that come out to be? So on the bottom I've got 5/3. So it's just 3. So this whole thing adds up to 3. So sorry if this is a little too quick or whatever, but you can pause the video and figure that out if you want. So the answer to this one is 3. Okay, alright. Things are going well. And what about C? Well, okay, so C is not geometric. C is the harmonic series. You just have to recognize it, and you have to have memorized that the harmonic series diverges. You don't have to. If you don't know that the harmonic series diverges, you're in serious trouble. I mean, you could take the Stephen Hawking approach and reinvent mathematics at the time that you're taking the exam, but I don't recommend it, even though that's the favored strategy. It's not the best strategy. Just remember that the harmonic series diverges. So this one diverges. Okay, and what about this one? Okay, so last time when we were just doing the sequences, arctan was very friendly and converged for us, but now we're adding them up. We saw in the previous problem that as n gets big, arctan gets close to pi over 2. What we're essentially doing here is adding up infinitely many pi over 2's, and so that adds up to an infinitely large number. If you want to be a little bit more formal, okay, so the answer is diverges. If you want to be a little bit more formal, or you want a more careful explanation of why D diverges, you can reflect on the fact that you could use the test for divergence. So remember, the test for divergence is the simplest test there is to see whether or not a series converges or diverges. It doesn't always work, but when it works, it's great. So you have an here, okay? So you know that if that the absolute value of n does not go to 0, then the series diverges. So which one do you like better? Okay, do you like actually seeing that D here, you're adding up pi over 2 infinitely many times? It's approximately equal to pi over 2 plus pi over 2 plus pi over 2 plus pi over 2 plus pi over 2. Okay, so when you add up some definite amount infinitely many times, it definitely equals infinity, so that gives you diverges, right? Or if you prefer formal explanations of things and you really followed the proof of this in the book and this is your favorite way to think of things, just use the test for divergence and just see that the terms are not going to 0, and that's all you need to know. If the terms don't go to 0, then it diverges. Okay, alright, so let's go on to E here. Okay, so this one is maybe a little bit tricky. You see the cosine, and that makes you think, well, the values are bouncing around, but that's not what's going on here, because its cosine of 1 is just some definite number, right? You could check that on your calculator. What is cosine of 1? You tell me. It's like 0.7 or something, right? So this is actually a geometric series. Let me write it down here like this. So cosine of 1 is some decimal number, and we're raising it to higher and higher powers. In fact, so that I can write it in the standard geometric form, I want to write it in the standard geometric form. So I'm going to factor out 1 cosine of 1. I can do that. So factoring still works with series. You can factor it out of infinitely many terms at once, which is kind of amazing. And alright, so what I have here is cosine of 1 times a convergent geometric series, because of course this